Well, we're going to learn some more stuff, and we're going to learn we're going to learn about Fisher's LSD procedure, which actually has a little bit of a scandalous name if you were to interpret that incorrectly. But in statistics, Fisher's LSD procedure stands for the least significant difference, and it provides a way to do something that when I show you the drawing, well, let's just read this, then I'll show you the drawing, but I'm going to preface the drawing. And then I still have to tell you about the James Audubon story. So if we were in person, I would say, help me remember to tell you about the James Audubon story, because by the time I get to the end of these slides, I'm usually like, I'm done. And just to remind us about the James Audubon story, I'm going to do a little bit of just a blank slide there. And then I'm going to take a picture of this. I can't do it easily with Windows. I can't easily take a picture like in a Mac. So I'm just going to come here, and what happens if I paste? There we go. So I pasted it in. And this will remind us to, and we'll just make it bigger. This will remind us to talk about that story. So now you don't have to remind me. All right, let's read this. Suppose that analysis of variance has provided statistical evidence. Statistical evidence, ladies and gentlemen, to reject the null hypothesis of equal population means. Fisher's least significant difference procedure can be used to determine where the differences occur. So, like, remember if we did, and the example that's going to be used is this Chem-Tech example. And so the Chem-Tech example is, right there. And they developed a new filtration system, and they have different methods for assembling it, and they have 3 methods, A, B, and C, and then they choose 15 workers, and they randomly assign 3 treatments to 5 workers. So worker 1 tries method A, B, and C. That's the treatment. That's the factor. Worker 2 tries method A, B, C. And then, worker 3, 4, 5, so on and so forth. You get the sample means. You get the sample variance. And then you get the sample standard deviation. And here we're doing analysis of variance to test for the quality of K population means with an experiment. When we do all of that, we get this right here. And so we get level of significance is 0.05, 95% confidence level. Our critical value is 3.89 because we have numerator degrees of freedom and we have denominator degrees of freedom. And if we remember, how do we calculate our test statistic? It's Mr. Mouse, so MSTR is in the mean square of treatments is in the numerator, and I just want to get a picture of that here for you. So mean square of treatments is in the numerator because where's the test statistic? The test statistic, I need to add that on here. The test statistic is MSTR over MSE. Let me find that. Hold on. Okay, so I'm adding that into our little table here. Oh no, I thought I copied it. I must press the wrong key. So let me come down here and we'll copy it again. And here's this test statistic. I'm going to do a control, make sure I'm pressing control C to copy it. It's really a little bit of a drag that my eyes can't see the keyboard like they used to or see the screen like they used to. I really relied on that, and now I got to figure that out, and these glasses aren't quite cutting it anymore. There's the test statistic, MSTR over Mr. Mouse, right? And here it is again, Mr. Mouse. That's how we get our F value. And that's our test statistic, so we could test that against a critical value. But I'm going to add the test statistic in here just as a little reminder. I'll put it down here in the corner. And now we have that test statistic up here on our terminology number 2 page. And I guess I should probably just add it throughout the rest wherever I have it. So I'm going to put it here. And I got to move it a little bit just out of the way because we have those notes down there. And then I think we referenced that slide one more time in here. And there it is again. So I'll put it down over here too. And that way, next time I go through this presentation with the class, it's in all the places. It's in all the places, not just some of the places, but all the places. So what are we talking about, right? This one's breaking my mind a little bit. Not literally, but it takes a moment to wrap your head around it. So we were talking about, let me find it, just one second. We were talking about the Kim test experiment. Here's the Kim test experiment as an example. And then, when we get our sample mean, our sample variance, we could start to calculate our values and get this. So at the 0.05 level of significance, it gives us 3.89 as a critical value. And then we calculate our test statistic, which we now know is calculated like that. And just for the heck of it, for fun's sake, I'll just put this down in the corner here, because isn't that fun? It's fun. And I'll just make it a little bit smaller and then bring it in a little bit more like that and then just put it down. So that's just a little bit of a reminder. So we get this as our test statistic, and we got that by figuring out what our MSTR is and what our MSE is, and we calculate our MSTR, which is between treatments, and our MSE, which is within treatments. We calculate those through all this procedure, and then once we have those, we could put MSTR over MSE, Mr. Mouse, and with Mr. Mouse, we get our F test statistic, and our F test statistic, we test that against the critical value. And so with the table, and the table that we're using here is the F table. So if I bring up the F table, so let me just go get that. And it's going to be in none of these tabs that I have open. So I have to open this. Just 1 second, I'll go get it just to expedite things. Hold on. Okay, here we go. So there's the F table. And if we come back to our presentation, we've got 2 degrees of freedom in the numerator and 12 degrees of freedom in the denominator. And so here we've got the numerator and we got 2 degrees of freedom, and here we have the denominator, we have 12 degrees of freedom, and we're at 0.05 level of significance. And that means we got 3.89 as a critical value. And we just calculated with Mr. Mouse a test statistic of 9.18, and that's in the reject area. And at 9.18 here is less than, like, what is that, 6.93. So we're less than 0.01. We're between 0 and 0.01. 0.01 is the p-value. So whether we use the p-value approach or the critical value approach, we are rejecting our null hypothesis that the population means are equal, and the population means are being approximated. We're making inferences about the population means with our sample data. So if we go back up here, here's our sample data. So the sample data gives us a sample mean, and we're using that sample mean to approximate the population mean. And what our null hypothesis asks is if each sample mean, right, that we get approximating, making an inference about the population mean from which this data came, right, if the sample means all equal each other, then the population means are going to equal each other. And the inference we can make is that our distribution looks like this, right? They all come from the same population mean. Even though they're different sample means, they're all coming from the same population mean. And if the null hypothesis isn't this, where the sample means making inferences about the population means, where the population means are all equal, if that null hypothesis is rejected, then what that means is that each sample mean is coming from a population, right? It's making inferences about the population mean, and the population mean has its own probability distribution. It has its own probability distribution. So the sample mean 1 has this probability distribution. It's making inferences about population mean 1. The sample mean 2 comes from this population. It's making inferences about the population mean, and it has this probability distribution, and same with 3. And that is that at least one of the means is not equal to the others, right? At least one of the means is not equal to the others. So we don't have the situation where all the means are equal. They're the same mean. We have a situation where at least one of these is not equal to the other means. They're coming from a different probability distribution. And what that means, when you look at your data, what that means is that, right, they aren't coming from the same population, and there's going to be one population probability distribution which is better. And so if this one's making 62 units a week, this is making 66 units a week, and this is making 52 units a week, like this one looks best. It's like doing the most units, and it has the least amount of variability. We're going with B, people. But maybe you want to prove that with statistics as opposed to just looking at it and making that decision. And so we do this analysis of variance, ANOVA, right? And we test for the quality of K population means. And we do that here for this experiment. And we find that we reject the null hypothesis. And it tells us, you know what? The sample means are making inferences about the population means. And we're rejecting the fact that all the population means are equal. One of them is not equal. So what do we do then? We could find out like a little bit more information about these population means by using Fisher's LSD procedure. Least significant difference procedure can be used to determine where the differences occur. Okay, and so maybe you'd need to do this if you had a lot of data and you couldn't just eyeball it, or it was really close and you couldn't quite tell by eyeballing it like we just eyeballed it. And so to figure out how to use Fisher's LSD procedure, I'm now going to show you a drawing. And this drawing is going to make me look like I've just invented nuclear physics, or I've figured out like how to do non-propulsion thrust in spacecraft. And so here's what this diagram looks like. And so a lot of this we already know. And really what you're looking at here is you're looking at something very similar to this, but we're using a new table, and the new table is the T table. And we have a new way of approaching this. So we're going to start by looking at our level of significance. And what we're really looking to see, our null hypothesis is mean one, is the mean for population 1 equal to the mean for population 2. And our alternative hypothesis is that they're not equal. And we're going to do this at the 0.05 level of significance. And so what we're testing here is a two-tailed test. Okay, follow me. Because it could be like that they're different too much in a positive way if we subtract one from the other. It could be a really large positive value, or it could be a really large negative value. And it went too far positive, it went too far negative, and so we reject. So it's a two-tailed test, which means if we're at the 0.05 level of significance, we have half of our alpha in this tail, half of our alpha in this tail. Alpha divided by 2 is equal to 0.025, or 2.5%. 2.5% of our data is from here to the right, and then 2.5% of our data is from here to the left. That's alpha divided by 2 is equal to 0.025. So we have our p-value, 0.025 here and 0.025 here. And now you understand this part, the null and alternative hypotheses, and you also understand this part, the level of significance. Now to do Fisher's LSD procedure, we're going to use a t-table. And a t-table is just another one of these tables. So I'm going to close my F distribution, and I'm going to open up my t-table, because let's have t. Let's have t. So here's my t-table, and if I open up my t-table, you can see the t distribution is showing me from this point, right? There's a 0, and from this point, from t to the right is this area of probability. And if we read it, it says entries in the table give t values. I can't read. Entries in the table give t values for an area or probability in the upper tail of the t distribution. For example, 10 degrees of freedom and a 0.05 area in the upper tail. So 10 degrees of freedom and a 0.05 area in the upper tail. We have 1.82. So that's what you see here, 1.82, 10 degrees of freedom, and 5.05 area in the upper tail, 5% in the upper tail. 1.82 is the t-value. T-value here is 1.82. So with this, let me just get rid of that. Boom. With this, if we have a t-value, let's see, if we have a level of significance of 0.025 right here, and we're operating with certain degrees of freedom. And so the way that you do Fisher's LSD procedure, now remember, we don't have to understand all of the engineering that goes into a BMW to drive the BMW. We don't have to be the engineers. The engineers can create the BMW, and we could get in the BMW, and all we have to know how to do is drive it. We don't have to be the engineers who create Fisher's LSD procedure. We just have to know enough about it to get into the driver's seat and drive it. We don't have to be the engineers. We just have to drive it. So you just take on face value that, okay, this is the degrees of freedom you use when you're using Fisher's LSD procedure. So here are the degrees of freedom, ladies and gentlemen. The degrees of freedom are the degrees of freedom for air, for your SSE. And the SSE is the within part, not the between. And to calculate the degrees of freedom for SSE, it's the total number of observations minus the total number of factors or methods, right? So we had 5 workers, and each worker did 3 different assembly methods, A, B, and C, right? So we have 5 workers, and each worker did A, B, and C. So we have a total of 15 observations. 15 is our N, total number of observations, minus K, and K is the treatments or the factors. factors. We'll call it the treatments. Either one. And so we have 15 minus 3 is 12. That's our degrees of freedom. Now that we know our degrees of freedom, and we know that we're at the 0.05 level of significance, and we know that this is a two-tailed test, right, to either reject or not reject the null hypothesis, and we know that up here is our 0.025, knowing that we have 12 degrees of freedom, and then we're doing things at the 0.02, 12 degrees, and we have 0.025. Here's 0.025. Here's 12 degrees of freedom. We've got 2.179 as our t-value. You see that right there, 2.179. So we could put this down here, 2.179. We got 0.025 here. We got 2.179 there. We've got 0.025 here, and we could do a negative 2.179 because this is symmetrical. Okay, and that's just in the book. Again, you don't have to be the engineer that made it. You just have to be able to read the manual, understand a few things about it so you can drive it. And so this is symmetrical, and if it's up here, you could also just put it down here and kind of flip the logic. So we got this here, we got that there. Now we just have to figure out like what are the things we're testing. And there's a new test statistic. And that new test statistic is, let me find it. It's, I'm just looking to see if I have the formula. Here, is this it? I think this is it. Let me just bring it over. And I'm actually going to put it on this page. And so here it is. And let's see, I just want to confirm. Yep, that's it. All right, sweet. I'm going to shrink it down. I'm actually going to move this one over. And I'm going to put this up. And then I'm going to make this bigger. I guess that actually works really well, just like that. And I'm going to get a little text. Let's put a little text in there. And we'll test statistic, and we're going to just make that like bold, and we don't want that plural. We'll make it bold, and then we want that to be like bright yellow because that is the way you draw attention to things. So we're just going to shrink it down, and we're going to bring this over. Now it looks just official, doesn't it? It's like, of course that's the test statistic. It says so right there. Here's our test statistic. Notice it's T. We're using the T table, okay? And to get our test statistic, we do I and J are two different points, right? Two different means. So here's like I, here's J, and that is like here's I and here's J, or maybe here's I and here's J, or maybe here's I and here's J. But what we're doing is we're taking the mean of one of the factors, one of the treatments, okay, and we're subtracting the mean of that treatment, and then we divide it by the square root of MSE, and so MSE for that is 28.33. Let me go find it so I can show it to you. All right, so I just scrolled back up to this example, and here you can see MSE being calculated, and it's 28.33, and you could also see the ANOVA table right here, and it's 28.33. And I'm just going to bring all these down and drop them at the end for reference. So that's all the ChemTech experiment. And I'm just going to make that, let's see, is that up here? I'm going to just make this bright. And I'm going to make it all bold. And I'm going to make it all green so that when people come here, when I come here, that's not what I wanted. When people come here, I just need to copy this. Copy that, and now put that here. Now it did what I wanted, and then I'm going to bring that over like that, and just a little bit more. Bring that over like that, and there we go. This is all the ChemTech experiment, and same with this one here. We'll just put that here, and just like that. This is all the ChemTech experiment. That's great. All right, so right, what we came here to see was our MSE is 28.33, and our MSE is 28.33. You can see it right there in the ANOVA table. And now it's handy if we need to jump back down to it. So we have our MSE of 28.33 right here, right? That's your MSE, your mean square for errors. And then you have 1 over Ni and 1 over Nj, and add to 1 over Nj. And remember, I and J, if we're doing 62 minus 66, 62 minus 66, right? That's our I, that's our J. Then 1 over N is how many were in that sample? There were 5 in that sample. And how many were in, that's the I sample. We're just like saying one versus the other. That's the IJ notation. And here's the other one, the J, and that's 5 in this sample. So we get 1 over 5, 1 over 5. So we get 62 minus 66, the mean of one of the one of the treatments, right? Minus the mean of the other treatment, all divided by the square root of the MSE of the whole shebang. And then we have 1 over how many were in that first treatment. How many were in that second treatment? I'm like factor treatment in my head. And then we do that math, we get negative 1.9. So we compare 62 minus 66. We compare 62 minus 52. We compare 66 minus 52, 66 minus 52. And when we do that, we get these numbers, negative 1.9, 2.971, and 4.16. These are t-values. These are test statistics. We could come down here and put them on this row with our t-values. Here's negative 1.9, negative 1.9. Here is 2.971, 2.971. Here's 4.16, here's 4.16. Looking at this graph, we can see we do not reject the 62 to 66. The difference between those two, we do not reject the null hypothesis. We say those population means are equal. So here, those population means are equal. They're coming from the same population, okay? And here with 62 minus 52 and 66 minus 52, so 62 minus 52 and 66 minus 52, right? Both of those produce 2.971 as a t-value and 4.16. We put them here. You can see that they are past our critical value. These test statistics are past our critical value. They're in the reject area. We reject both of these. And we say, right? And so we say that here we're rejecting the null hypothesis that the population means are equal. And we can say the population means aren't equal, which tells us that we're in this type of a situation, right? Where, you know, the population means aren't equal. So we have a sample and it, you know, two samples, and they're coming from different probability distributions with different population means. I feel like I should start that Pink Floyd song, you know, that starts with a big sigh. When I sigh like that, I'm like, I want to hear that song. Great. So now we're understanding this in the framework of what we already know. And when we have these t-values, we could come back here to our table. And at our table with 12 degrees of freedom right here, at our table with 12 degrees of freedom, we could look for where is 12 degrees of freedom, where is the t-value 2.91 come in? 2.91 is going to be between 0.01 and 0.05. You see that? That's 2.91 is going to be between those two. And so we could say that's between the 0.01 and the 0.05. 0.01 is 1% and 0.005 is 0.5%. So it's like, you know, it's that area. It's here, all the data is from, that percentage of data is from here to the right. And we can also look for 4.16 at 12 degrees of freedom. 4.16 is going to be, you know, out here. So it's going to be less than 0.5%. And so here we have 0.5% to 0, right? And, you know, it's out there. And then for this other one, which was negative 1.19, 1.19 at 12 degrees of freedom is going to be between 20 and 0.2 and 0.1, or 20% and 10%. That's where 1.19 is. And because this is symmetrical reflexive, we could say negative 1.19, same thing. And here's 10 to 20% of our data is from here to the left, and 2.5% of our data is from here to left, right? So now we have our t-values, we have our p-values. We could use the p-value approach, we could use the critical value approach, and we know whether to reject or do not reject the null hypotheses. All of that is the setup for understanding Fisher's LSD procedure, okay? Because Fisher's LSD procedure is just another way to kind of mathematically look at the same thing. And so here's the formula for Fisher's LSD procedure. It is T alpha over 2, okay? And so we already calculate that. That's our 2.179. Here's our 2.179. And then it's this stuff from the denominator right here, the MSE multiplied by parentheses 1 over Ni plus 1 over Nj. Here's MSE multiplied by parentheses 1 over Ni, 1 over Nj, the square root of that. And when we stick in our numbers, we get 28.33 here multiplied by that. I calculated that right here, gives you, what is that? 3.3663. So up here, I just wrote it out like this, but then I just used a 3.3663. And so that calculates to that after you've like taken the square root and everything, multiplied it, added it, multiplied it, and then taken the square root. You get 3.663 times 2.179, which is this, our T alpha over 2. We get 7.34 as our LSD. Okay, that's our LSD, least squared denominator. And now what Fisher's LSD thing says is you could figure out, get your LSD, and that becomes kind of like a critical value, and you could test, have a test statistic, you could test against that critical value. And so your test statistic is going to be the absolute value of the difference between means. And so up here we did 62 minus 66, here's 62 minus 66. Up here we did 62 minus 52, here's 62 minus 52. Here we did 66 minus 52, here's 66 minus 52. And forgive me if I said some of those wrongs, because my eyes maybe aren't what they used to be. So we get -4, 10, and 14. And then we reject if the absolute value of the difference between two means for each of the treatments, mean for each of the treatments, is greater or equal to our LSD critical value, right? And so our LSD critical value is 7.34. We get the absolute value of -4, 10, and 14, which is 4, 10, and 14. 4 is less than 7.34, do not reject. Same conclusion, right? Here's do not reject for 62 minus 66. Here's do not reject looking at it with Fisher's LSD procedure. And then we have 10, which is greater than 7.34, and we have 14, which is greater than 7.34. And so for these situations, 62 minus 52 and 66 minus 52, we do reject. We do reject. And that's Fisher's LSD procedure. Quite frankly, I like this p-value and critical value approach, drawing it out. Like I will sit there for 5 minutes, 10 minutes at my desk to draw it out because I'm a visual person. And I like the visual approach to it. So that's how Fisher's LSD procedure works. And I wanted to explain it to you like this because now we're going to look at the slides. And we're going to look at the slides in the PowerPoint presentation. And if you hadn't, I don't know why I say PowerPoint, this is Google Slides. If you hadn't seen this right here, you would be like, what is going on? Just like the first time I looked at this, I was like, what is going on? And it's only after I read about it and I looked up other documents, right? So here I looked up here I did some calculations, and then I looked up this document, which is like, from, where's this from? It's from University of Dallas, right? And I read about this here, and then I asked ChatGPT about it. So you can pause the video here, and you can read ChatGPT. ChatGPT came up with a different formula. So hey, maybe there's a different formula that you can use, right? And you can pause the video here, and you can also read about that. Geez, I'm telling you. So and then I also read the book, and it's only after all that, and I drew this diagram, and I'm like, okay, I kind of understand how to drive this, even if I don't understand all of the engineering behind it. But it does kind of look like I've invented like non-propulsion flight for UFOs here, right? Like it's pretty lot of it looks like fancy stuff, like we're doing college level stuff here. All right, so multiple comparison procedures. Suppose that analysis of variance has provided statistical. Now we're going to look at the Google Slides. Has provided statistical evidence to reject the null hypothesis of equal population means. And that's what we got down here, right? When we did this other example. So the other example is this one. We ended up coming up with the conclusion that we needed to reject it. And I'm wondering if the conclusion's here, but we have to go all the way up here and just like proof's in the pudding. So let's go take a look at it. And where's the example? It's right there. And there, and then here we reject, right? This is what we ended up getting. Test statistic of 9.81, and so we reject. And so, coming back down here to Fisher's LSD, we have got that analysis of variance, ANOVA, provided statistical evidence to reject the null hypothesis of equal population means. Fisher's least significant difference procedure can be used to determine where the differences occur. Okay, and so they do the hypotheses. That's what we've got here, hypotheses that the means are equal. And then they do the test statistic. And I'm going to bold this, and I'm going to highlight it. Cool. And that's exactly what we have right here on our drawing. So all good so far. And then they provide us a rejection rule. And here it says where the value of t alpha over 2 is based on t distribution with nt minus k degrees of freedom. And so it's your total number in your sample minus how many treatments there were in the sample, and that's what we did for our degrees of freedom right here, right? And so that's the degrees of freedom. And then you come down here and Fisher's LSD procedure, it's like we see the hypothesis again. They just showed this to us, but now they tell us the test statistic is this. And here's another rejection rule. And here's where LSD is equal to that. And that's where it gets a little confusing, because if you put all this on the same page, right? And let's do that. So I'm going to grab all this and I'm going to copy it. Actually, I'm just going to make it smaller. Can I make it smaller? Like, does everything get smaller? It doesn't. So I have to undo that, and then I have to just select these, and then I have to make these like 14, and then I'm going to shift these over, and let's just see if those are in good places. Those are in pretty good places. And now I'm going to grab all this and bring it up over here. I'm going to move these. Oops, I didn't want to move that. I want to move these. Oh, and I want this one too. Give me that one. And I'm going to move these guys over. And then I'm going to paste all this in. I'm going to move all this over to the right. Okay, so they tell us hypothesis. Cool, right? And then here's the test statistic. T is that. And then here they give us this, and we can see this down here, the rejection rule. So this is like, you know, still a little bit hard for me to grok. And the test statistic here gave us these values, which went down right there. The negative 1.19, 2.1, oh, I did a little transpose stuff, 2.971, 2.179. That's funny. I don't usually do that. And then here, oh, no, that's the 2.179. That's funny. They are transposed a little bit. Here's the 2.971, and here's the 4.176, or the 4.16. There we go. And so that gives us our test statistic, our t-value for here. Good to know. And then this one here gives us, like, you know, this value here, where we did the LSD thing right there. And then this one here, the test statistic, is to test against this being our critical value, right? Using Fisher's LSD. So I'm going to put this like over here, and actually, yeah, why not? I'll copy this, and I'll see what happens when I paste it like that. Oh, that's so nice. It did work. I pasted it without formatting, and then I'm going to make this one bold, and I'm going to make this one green, because this is like Fisher's LSD procedure here, where this is your test statistic, and you're testing it against this critical value. And I'm just going to call this one here, I'm just going to bring it down a little bit, and I'm going to get another little test, and I'm going to say this is the critical value. Whoop. And we'll make that like 12, because I think that ones are 12. Maybe they're 14. 14, and we'll make it bold, and then we'll make it yellow. Okay, because to me that's the critical value. And this one over here, we'll do like this one over here is like the graphing it out way. But they don't explain this. I'm going to just call this the graphing it out way. You know, and that's we'll just say that's Todd speak. Todd's definition. And I think we need to do it like this. Boop, 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 boop. And we'll call it Todd's phrase. Todd's phrase. Todd's phrase. Todd's phrase. Todd's phrase. There we go, the graphing it out way. Because this is the graphing it out way, right? Like, we got our t-values, and we graphed it out, and we got our p-values. And so you could call it the critical value approach. But even here, they're calling critical value test statistic. So that confused me when I was looking through these. I'm like, why are they giving me two test statistics? What's going on? And then we have this rejection rule, and I think I'd like to see that rejection rule on this page, but I already got a lot happening here. So p-value approach, and you know, I'm not into just like these rules. They don't totally click with me, so whatever. Pause it if it works for you and read it. Here we go. And so here's the example we already did, and I put this here. No. Yeah, so the Chemtech, recall the Chemtech experiment where the managers wanted to know if there's a difference in mean number of units produced per week when different assembly methods are used, right? Analysis of variances provides statistical evidence to reject the null hypothesis of equal population means. Fisher's least significant difference procedure can be used to determine where the differences occur. Cool, right? It's kind of what we already know. And so here is their calculation, and they get 7.34 for their LSD, and 7.34 for the LSD, same as us, right? And you know, what I really like about this, you could see how it's like connected, right? You got your T alpha over 2, your 2.179, and you have your MSE multiplied by this, take the square root of it up here in this stuff, and then you also have it down here. So you can kind of see some of the engineering, like, oh, all right, I see where they got that stuff, right? And there's a mosquito buzz in my feet. Don't care for it. And then here, you get your test statistic, which is the absolute value. You take the difference between means. And if this is greater than or equal to 7.34, you reject. But this one, you know, the mean number of units produced per week for method A is equal to the population mean for method B. So we'll put population mean number of units produced per week for method A is equal to the population mean for method B. Population mean, I would like to say population mean for method A is equal to the population mean. I see what they're getting at. That's fine. The population mean number of units produced per week for method A is equal to population mean is equal to that's fine. I like it. And then here is 66 minus 52. So 66 minus 52 is right here, this lower one, and 66 minus 52 is here. So if you do it this way, the critical value approach, the p-value approach, or if you do it the LSD approach, you know, where this is your test statistic and this is your critical value, you're also going to get 66 minus 52. The mean number of units produced per week for method B is not equal to the population mean. You know, population mean number of units produced per week for method B is not equal to population mean for method C. So those two are not equal. So you can see which ones aren't equal and which ones are if the analysis of variance shows that, hey, one of them is not equal. And then here's 62. Did we do that one? 66 minus 52. And here's 62 minus 52. And it's the same thing. These are not equal either. Is not equal, not equal. So I'm just going to highlight that. Boom. And we'll make that one bright yellow. And we'll highlight this one. And boom. And we'll make that one bright yellow. And we'll highlight this one. Kaboom. And we'll put is equal to. And we'll make that bright yellow. Kaboom. Oh dear, ladies and gentlemen. And then finally we have our last here where they say a little caveat about, you know, you could get type 1 error rates. And type 1 error rates is a false positive. So false positive, if we look up the error rates, type 1 error, right? So false positive is that in reality it's false, but your measurement says it's true. And so you could get false positives here where, you know, in reality it's false, but your data says it's true. So comparison-wise type 1 error, the comparison-wise type 1 error rate alpha indicates the level of significance associated with a single pairwise comparison. And so that is like our level of significance alpha, I think. The experiment-wise type 1 error rate alpha EW, experiment-wise, I guess EW, is the probability of making a type 1 error on at least one of the k-1 pairwise comparisons. So if we have 3 treatments, it's going to be 3 minus 1 factorial. So 2 factorial is going to be 2 times 1, it's going to be 2, right? So we'll have, it's the probability of making a type 1 error on at least one of the 2 pairwise comparisons. Interesting. And alpha EW is equal to 1 minus alpha to this power. The experiment-wise type 1 error rate gets larger for problems with more populations, for a larger k with more populations, so more treatments, right? So we increase the likelihood of a type 1 error if we have, like, you know, we had 3 treatments, 3 Ks, but what if we had like 30? We're going to increase our type 1 error. I guess logically, if you think about that, you know, that kind of makes sense. But that's just like another little piece. You ready for the Audubon story? I don't know if this story is true, but we should ask ChatGPT. So let me get ChatGPT. And ChatGPT, here boy, here. Come here, ChatGPT. Come here. Come on, ChatGPT. There's ChatGPT. And we're going to get this quote, and we're going to copy all that text, and we're going to put that in. And then we're going to say, well, we'll say this. Was it James Audubon who thought he was a failure in life? and then decided to take a year, walk around America, and draw pictures of birds in his notebook, which is something he always loved doing. Then, in doing this, his book with his drawings made him famous, and he became one of the early, if not the earliest, founders of some field that encompasses studying animals and nature. Do you know this story? Is this the story of James Audubon? I think it is. Anyhow, the story is like this guy was just like he tried, and he failed, and he was so down on himself. He said, you know, I'm kind of done, and he contemplated suicide. And he said, but before I do that, I'm just going to take a year and I'm just going to walk around, so I don't make a rash decision. I'm just going to walk around and draw in my book and draw pictures of birds, and that's something I love, so I'm going to give that to myself. And so he did that, and I think he rekindled his love for life, and then he published his book, and he became the founder of like a field, and he became super famous, and I guess you could say he achieved success, which is interesting. And you know, it's great. It's a great story. But what's interesting about it is how perspective, really, your mental perspective, can make you happy or unhappy. Like you do that to yourself. We do that to ourselves. You know, we do that to ourselves. And if we just say, you know what, every day I'm doing good, I'm pushing the ball forward, I worked hard, I'm a good person, I was kind to people, you know, you sing your own praises when you go to bed at night to counter that negativity bias. You know, you just kind of think about what you did that day that you're proud of yourself for. And you give yourself some kudos for that. And you keep pushing forward, and you say to yourself, I'm a good person. I helped those people out. You know, I picked up some trash. And you do things to make yourself feel good. And you remind yourself of those things because you gotta. Because we come with that pre-built negativity bias, which I told you about in a previous video. So let's see if this is the story of James Audubon. Yes, you're recalling the story of James Audubon. Not James Audubon. What is it? John James Audubon, not James Audubon, though the details near memory are close. John James Audubon was an American ornithologist, naturalist, and painter known for incredible depictions of birds in his books. The Birds of America's 1827 to 1838, which made him famous. Audubon faced many struggles and financial difficulties early in his life. He tried several business ventures, many of which failed, leading to him feel like a failure. However, he had always been passionate about birds and nature. And hold on one second. Right on. So, he had always been passionate about birds and nature. In the early 1820s, after a string of failed businesses and facing significant financial hardship, he decided to devote himself fully to his true passion, documenting and painting birds. He traveled extensively across America, observing and drawing birds in their natural habitats, often going on long treks to remote areas. His work culminated in The Birds of America, a massive and beautifully illustrated book of 435 life-size prints of North American birds, which is considered one of the finest ornithological works ever. Here we go. Come on. Ornithology. Where's my chat? Works ever completed. The book earned him widespread acclaim and established him as a pioneer in the field of ornithology, the study of birds, as well as one of the earliest influential figures in the broader study of animals and nature. So yes, in essence, Audubon's journey from hardship to success came through his deep love of birds and nature, and his artistic dedication to documenting them helped found modern bird and nature studies. So John James Audubon. And then he also said, when the book and the bird disagree, when the bird and the book disagree, always believe the bird. Right? And I love that quote because it means that we get some information from the book and the book tells us stuff, but when you're actually out in the real world and you're doing something and you see things which don't make sense in relation to the book, You investigate it and you believe what is happening in the real world. You don't believe what's written in the book or what's already printed in the book. So we're going to take a quick look at some of his drawings. And here we go, man. Like, look at how beautiful those are. Well, here he is. Like, just, you know, that was a life that, where'd he go? That was a life that was lived. You know, he's got his little gun and, you know, like he had his challenges. He thought he was a failure and then he became successful and he started an entire field in academia. And maybe this is like, you know, some of the pictures here. Like, look at how gorgeous that is. You know, how pretty. And so here, you know, we've got some more, but just like, wow, so beautiful. You know, it's like got a real style. Like you could decorate your house in Florida with these and be all Tommy Bahama looking. But anyhow, that's John James Audubon. And there's also now the Audubon Foundation. The Audubon Foundation has something to do with animals and birds and things like that. Makes me almost want to get one of these prints and like put it up somewhere. Isn't that pretty? Can we make that bigger? Wow, look at how gorgeous that is. That's so cool. I don't know what this is here. Oh, so this shows you like, you know, the size of it, like if you were to put it somewhere. But yeah, all right. Statistics. That was a doozy. I don't know, you know, took some explaining to figure that out. But look, we're already all the way at the end of part B for chapter 13. Part A of chapter 13. Now all we have is part B. See you in part B.